Hey, so have we seen a trig graph before?
Yes.
Do you recall what they look like?
Squiggles.
Squiggles. I mean, that's an accurate description. So yes, squiggles would kind of be what they look like. So some places that you may have seen them before, like my daughter's actually doing them right now in her 6th grade science class. They don't call them that because they're going over waves. So like sound waves, light waves, all those types of things. All of those have trig type graphs that represent them. Because basically our trig graphs look like waves or squiggles. So let's go over. Alright, so let's go over basically how we find our sine function values. So remember back to like pre-algebra, when we first started doing graphs, we would make a chart and just plot a bunch of values, kind of get the shape of the graph. So if I have y equals sine of x as my function, okay, what type of values do we want to plug into x?
Numbers between 0 and 9.
Okay, so like 1, 2, 3, 4, 5.
Whole numbers.
Do we know what sine of 1 is? Or sine of 2? No? Are we going to get very nice answers? No. What would be a number that we would get a nice answer for?
30.
30, right? Because 30 is one of our special what? Angles. So x represents angles when I'm dealing with trig functions. So we want to choose our values strategically. That way we know what our sine or cosine or so forth is. However, I'm going to burst your bubble now. Whenever we graph things, we are going to graph everything in radians. So we will be in radians most of the time. Okay? And then, thinking about it, so what's that thing that Mrs. Bennett told you that you needed to have memorized because we're going to use it a lot?
Unit circle.
The unit circle. So we're going to use our unit circle to find those values. So remember that we have 3 main special angles in our first quadrant, and then we have points. So we have 1, 0, square root of 3 over 2, comma 1/2, square root of 2 over 2, comma square root of 2 over 2, and then 1/2, comma square root of 3 over 2, and then 0, comma 1. So if we're looking for our sine values, are we wanting to look at our x values or our y values?
What?
Our y values. So we're going to start with 0. 0. So sine of 0 is what? So this would be my 0. I'm looking at my y values. I get 0. 0. So that's my output. So then what's my next angle? 30. In radians. Pi over 6. Okay, and then what is our output in that one?
1/2.
What's our next angle?
Pi over 4.
Agreed. And what do we get?
Square root of 2 over 2.
Okay. Now, whenever we're graphing, we're going to be plotting points. Is it going to be easy to plot square root of 2 over 2? So what might it be helpful to have? What would be easier to plot?
I didn't know if that was allowed.
Yeah. We could plot the decimal approximation, right? And it should be about 0.7. Does that make sense? So then from there, notice that if I were to use pi over 3, I would get square root of 3 over 2, which is also going to be a really ugly decimal. Remember that whenever we're graphing a graph and we're plotting points, we can pick which points we want to plot, right? And because it's going to be continuous, the rest of these values are going to be filled in whenever we start connecting stuff, okay? So I'm going to pick values that are going to be nice for me to graph just because it's going to be easier to plot on the actual graph. So I'm going to go ahead and skip pi over 3, but realize like you could put it on your chart if you really wanted to. So our next value is going to be pi over 2. And what do we get at pi over 2?
1.
1. Okay. So then notice we would go to our second quadrant. So what angle in our second quadrant has a reference angle of pi over 6?
Pi over 3.
Not quite.
No.
So remember that our reference angles are always just the denominator. Okay, so I need a 6 in my denominator in order to have pi over 6 as my reference angle.
5 over 6?
Yeah, 5 pi over 6. Because in our second quadrant, it is 1 less than the denominator for our numerator. You with me? Okay. So this 5 pi over 6 is going to have the same output as our pi over 6. And then we just need to decide is sine positive or negative in our second quadrant.
Positive.
It's positive. And again, we could include 3 pi over 4 and 2 pi over 3. But both of those are going to have square roots in them, so again, they would be not so fun decimals. I'm just going to skip those. So next up, we would have pi. What would we get for pi? Basically, it's going to be the opposite of our 0.
1.
And negative 1. It's going to be 0, right? Because it's still, it would be negative 1 comma 0. But remember that our sine value is our y value, and so our y value is still 0. So we still get that. Okay? Now, what is our reference angle for, what is our angle in the third quadrant that has a reference angle of pi over 6?
7 pi over 6.
Agreed.
I know some things.
And again, I'm going to get 1/2, but is sine positive or negative in my third quadrant? Negative. So then remember at 270 or 3 pi over 2. Now what would our value be?
1. Negative 1.
Negative 1 because we go down. So negative 1. And then in our fourth quadrant, we would get
11 pi over 6.
And it's also going to be negative 1/2. And then 2 pi is going to be the same thing as 0. We're going to get what? 0?
0.
Okay. Now, the special thing about sines and cosines, right, in any of our trig functions, is that they repeat themselves, right? So, like, from here, notice that if I were to keep going, I'm just going to get the same values all over again. Y'all with me? And so, basically, these are called periodic functions because they repeat themselves periodically. So every 2 pi, my sine function is going to give me out the same values. Does that kind of make sense? And so 2 pi is what we call the period of the function, or how often it repeats itself. Yeah? Okay. So let's put these values on a graph. So I'm going to go ahead and label my y-axis. I'm going to say that every square is 1/2, just to kind of give you some space. Now, what about my x-axis? What do I want to label them with? So want to label it 1, 2, 3, 4, 5?
Radians.
I want to label it in radians because to try and find the decimal approximation of pi over 6 would not be super fun. But as long as we are consistent in our labeling, we can label it in whatever unit we want to label it. Yes? So let's do 1, 2, 3, 4. So this would be 2 pi. So then halfway in between would be pi. And then I have pi over 2, 3 pi over 2. Okay? Now, just like with our other types of graphs that we've seen, so think about like your parabolas. When we graph our parabola, what is the first point that we always want to look for in our graph? With the parabola.
Either y-intercept or vertex.
Yeah, so usually it's our vertex, okay? Or sometimes our y-intercept might be helpful as well. And those are what we call key points. Okay, your vertex is an especially like important key point for your parabola. Our sine graph and our cosine graph have key points as well. And those are going to be the important points that basically give us the general shape of our graph. And those are going to be the ones that we want to look at first. So notice that my first and my last points are both zeros. Okay? And then notice that exactly halfway in between, so between 0 and 2 pi, I get pi, and I also have a 0. Then halfway in between 0 and pi, I have pi over 2. And I get an output of 1, which is our maximum value for sine. And then halfway in between pi and 2 pi is 3 pi over 2, and we get our minimum value. Are we all with me? And the reason why we pick those is because 1, zeros, maxes and mins are important. And then 2, notice that I said 2 pi is our period, and I'm going to show us how we find that here in a minute. And then basically all we have to do to find our other things is divide by 2. So like, I know that halfway in between, I divide 2 pi by 2, I get pi. I know that has to be my 0. I divide pi by 2, I get pi over 2. I know that has to be my max. So it's really easy to find those increments, and so that's why we usually label those. So we said that we start and end at what y value? What's our output? For our starting point and our ending point?
0.
Yes. And then we said halfway in between, we also have a 0. Then halfway in between our first 2 zeros, we have our maximum. And halfway in between our second 2 zeros, we have our minimum. And then notice that like if we wanted to plot it, so at like pi over 6, it would be 1/2, while pi over 6 is going to be partway in between 0 and pi over 2, a little bit closer to our 0, so it would be there. And we could also, again, to plot the rest of the points that we added, but like I said, those key points give us the basic shape. So we don't really have to graph all of those other points, which just makes our lives a whole lot easier. The big thing to remember about your sine and cosine graphs is that they are curves, so they're going to look more like parts of parabolas, not absolute values. So make sure that you like curve them off. So go like that. And then remember, like I said, it's going to repeat itself. And that means that it will also repeat itself in the negative direction. The only difference is because, remember, as we go negative, it would be going clockwise instead of counterclockwise. It gets like reversed, basically. So instead of going up first, I go down first. Because we would be going in that fourth quadrant, which has negative y values instead of positive y values. So that is our general shape, or the parent function, for our y equals sine of x graph. A couple of important things that we might want to point out. What is the domain of this graph?
Or reverse.
and then our range. One to negative one. Almost. Flip those.
Negative 1 to 1.
There we go. Yes. It is negative 1 to what? We want to put our smallest value first. So yes, all of our y values, notice, are in between. And like you said, because it's a periodic graph, even though I don't have the rest of the graph filled in, I know that it's going to continue in that same pattern. So I know that anywhere on my graph, my outputs or my y values have to be between negative 1 and 1. Questions on that? Yes, no, maybe?
No.
Alright, let's go ahead and look at our cosine graph next. And again, it's going to be very similar. I'm still using the unit circle, but this time, remember, for our unit circle, we want to use the x values instead. Okay, so if we plug in 0 for cosine, what do we get this time? So this time it's going to be 1. So notice that it's going to start up higher than what our sine graph does. So it's going to be a little bit different. Then, just like before, if we wanted to, we could plot, say, like pi over 4. And again, we get square root of 2 over 2, which is still 0.7. But 0.7 is not going to be super fun to try and graph. So we're going to stick with the angles that would give us whole numbers or fractional numbers that we can evaluate. So our next point would be at pi over 3. What do we get at pi over 3? 1 half. So notice this time, instead of using angles that have reference angles of pi's over 6's, I want to use angles that have reference angles of pi's over 3's, because those are going to give me the 1 halves. So then my next one would be pi over 2. What do we get there?
0.
Agreed. What about at 2 pi over 3?
1 half.
Almost.
Negative.
There you go. In our second quadrant, remember that cosine is negative, so we would get negative 1 half. And then what would we get at pi?
Negative 1.
Or pi over 2?
Negative 1 half.
And then we get
0.
0. Then we get positive 1 half. And then again, we start all the way back over, same thing that we got at 0, at 1. So again, let's look at kind of our pattern that we have for cosine. So notice that this time we start and end at a maximum value. Exactly halfway in between is going to be our minimum value, and then halfway in between your mins and your maxes are going to be your zeros. So again, those are going to be the key points that we want to look at. Questions on that? Okay, so let's look at that graph again. So again, I'm going to label my units. So what did we say our cosine graph starts at? 1. So remember we said it starts at 1, and then it also ends at 1. And then we said exactly halfway in between, which would be at pi, is our minimum value. And then halfway in between each of those are going to be our zeros. Okay, and then we're just going to kind of connect them. them all just like I did before. And so that would be our graph. And again, because it's a periodic function, I know that going the opposite direction, it's going to repeat itself, but it basically does it backwards because we would be going clockwise instead of counterclockwise. Questions on that? So notice that this graph is really similar to our sine graph. Basically, we've kind of just like shifted everything over a little bit. So what is our domain for this graph?
All real numbers.
It's still all real numbers, and our range?
-1 to 1.
It's still -1 to 1. So that part didn't change. But now, in most of the time, for our graphs, are we just going to look at our parent functions when we graph things? No, usually we want to do some like transformations with them, yes? So we're going to look at kind of our first two transformations today, and then we'll look at our next two transformations next time. So our first two transformations are going to be this value on the outside and this value on the inside. So let's play around a little bit with what that does. So our normal sine graph looks like that. We have a maximum at 1, a minimum at -1, and it kind of like looks like a little wave in between. So if we were to multiply, say, 2 on the outside, what do we think that that would do? So think about maybe like if you had your slope of just a normal line. If I go from a slope of 1 to a slope of 2, what's that going to do to the graph? Yeah, it's going to stretch it. It makes it steeper, which is going to do something very similar here. Just when I stretch it, it's going to stretch the whole graph, which makes it come up taller. So what point do we think our new maximum is at? It is. It's at 2. And then our minimum is now at -2. So what do we think the 4 would do?
The same thing but more.
The same thing but more. Now we're at a maximum of 4 and a minimum of -4. What about if I multiplied it by something that's less than 1, like a half? It's going to compress it, or basically make it smaller. So now my maximum is at 1/2, and my minimum is at -1/2. Okay? The only other thing that we could see, so notice as we get bigger numbers in the front, I get a bigger graph. Once I go to a fraction or decimal smaller than 1, I get a smaller graph. But what do you think happens when my numbers go negative?
It flips.
It flips. It's going to reflect it. So basically, instead of going up first, I go down first. Okay. Now, for our cosine graph, it's going to be quite similar. So there's my cosine graph. My 4 and my 2 on the outside are going to stretch it. My 1/2 is going to compress it. Okay? But now let's look at our numbers on the inside. So here's my normal graph. What do we think multiplying by something on the inside of our graph is going to do?
Is it going to like keep the range the same,
It does.
or do you stretch it like inside of the graph?
It gets more wiggly.
Yeah.
Yes.
Yeah. Yeah.
Yes, I like that way. Yes, it gets more wiggly. So basically, think about it as if I multiply on the outside, right? I'm stretching or compressing it vertically. So if I'm multiplying it on the inside, it's going to stretch or compress it horizontally. So you can kind of think about it like an accordion. Like as I squish it, I'm going to get more of them. As I stretch it, I get less wiggles in a certain space. But which one do we think makes more or makes less? So like if I multiply it by a 2, do you think that's going to make more squiggles or like less squiggles?
Less.
I think less.
Oh.
Well then.
So normally we would think it would be less because we would be stretching it, right, when we multiply by a 2. But notice that when I go from 2 to 4, I get even more. And that when I go to 1/2, I get less. So our b value has the opposite or the inverse relation to what our normal value on the outside does. Does that kind of make sense? Because that's going to be important here in a second. And it's going to be really similar with our cosine as well. So notice as I multiply by bigger numbers, I get more. As I multiply by fractional numbers, I get less. So here's a question. What is going to happen if we make our b value negative? So multiplying by a negative on the outside, remember, reflects it vertically, right? So what would this reflect it?
Horizontally.
Horizontally, okay? But if I reflect it horizontally, so we'll get negative 0.5, I get the same thing, right? As if I had just 1/2. Well, because think about it, it's periodic, so if I reflect the whole thing, it's the same thing. And so it's symmetric about our y-axis. So putting a negative in front of it, it's not going to, on the inside of the function, isn't going to change it. But putting a negative on the outside is. It's going to make it go up first instead of down. Alright, so let's kind of put all of that together. Okay, so look at kind of what that means for us. So I talked a little bit about this word called the period of a graph. Okay, so the period of the graph, remember, is how frequently something repeats itself. Okay, then the other thing that we're going to look at is the amplitude, which is the other thing that we looked at, which is how far it's been stretched or compressed. So our amplitude is going to be half the distance between the maximum and minimum. And when we're looking at our function, okay, our amplitude is going to equal the absolute value of a. So whatever that number on the outside of our function is. And the reason it's half the distance is because remember when I stretch it both directions. So when I multiplied by 2, I not only went up to +2, but I also went down to -2. So technically the distance between my max and my min would be 4, but we would say that our amplitude is 2. Does that make sense? Okay. Now, the period of a graph is going to be the distance it takes to complete a full cycle. Which is basically where we get back to kind of where we started with. So now, what did we say that the normal period of the graph is? How long does it take for it to repeat itself?
2 pi.
2 pi. Okay. And then what did we say about our b value? That it has what type of relationship? Because it did the opposite of what we thought it would do, right?
Inverse.
An inverse relationship, right? And remember that an inverse relationship means that we have division instead of multiplication. So to find the new period of a graph, we would divide by the b value, which is that inside number, not multiply it. So be careful on that one.